Hello, everyone. In this section, we're going to study the equation of the tangent line for a function f of x at a point x equal a. If you remember correctly, so far, we only use the slope of the tangent line. And one thing that you should master at this point is if you have a function f of x at a point x equal a inside the domain of the function, if the slope of the tangent line is strictly positive, it means that the function is increasing. If the slope of the tangent line is strictly negative, it means that the function is decreasing. If the slope of the tangent line is either 0 or does not exist / undefined, it means you have a critical point for your function. And for a critical point, maybe you have a local maximum, local minimum, or it could be still just increasing or decreasing. It depends. You just don't know when you're at a critical point. Now, in this section, what we want to do is study the equation of the tangent line, not just the slope, but the actual equation y equal mx plus b. And that equation is going to be super important because we're going to use it to approximate outputs for the function f of x around nice points inside the domain of that function. We'll see those examples very soon. So let's start with the definition. So if you start with a function, a point A inside the domain of that function, suppose that f prime of a exists, so it's a number, then the tangent line for the function f of x at x equal a is the linear equation y equal mx plus b. So we're computing here lines, equations of lines, so very simple objects with the following properties. First, that line passes through the point AF of A. This is going to be super important because we're going to use this to compute the B value. And then, of course, the slope of that line is the value of the derivative at x equal A. So it's equal to f prime at A. So in a nutshell, the equation of the tangent line, the slope, of course, of that line is going to be the value of the derivative. And then to figure out the b value, we're just going to use the fact that we know one point on that line, and that point is a f of a. So let's just do some examples very quickly. First example, suppose the function f of x is x squared minus 8x plus 9. Let's find the equation of the tangent line of that function at x equal 3. So here's the solution. The first thing I always do when I construct the equation of the tangent line for a function, I first evaluate my function. So here, let's compute f at 3. So this is just an evaluation process. So we get 3 squared minus 8 times 3 plus 9. And if you do the math correctly, you're going to get minus 6. So we need the output. Then the next step is to compute the derivative of f. So let's compute f prime at x. So here we just need basic differentiation. The derivative of x squared is 2x. The derivative of minus 8x is minus 8. And then the derivative of 9 is 0. So we have f prime. And then as soon as you have the derivative, you compute the slope of the tangent line by computing its output. So here m is going to be f prime at 3, so 2 times 3 minus 8, which simplifies to minus 2. So at this point, we know that the equation of the tangent line is of the form L of x is equal to m, which is known now to be minus 2, x plus b. We don't know what b is yet, but we know that this line is passing through, or passing by, and you just write the point here. So the point is 3 minus 6. 3 because this is specified in the question, so we're doing this at 3. And the y value, and this is why I've computed the output right away, is just the output of the function f at 3. In this case, we got minus 6. So now this is just a plug and play. So you replace x by 3 and y by minus 6. So you get the following information. So you get minus 6 is equal to minus 2 times 3 plus b. And if you isolate b here, you will see that b is equal to 0. So we know what m is, we know what b is, so therefore the equation of the tangent line for that function at x equals 3 is minus 2x. Whoop, just forgot my minus there. All right, and that's my equation of my tangent line. And here, as a remark, what I've done for you, okay, I've drawn the function x squared minus 8x plus 9, and I've also drawn the equation y equal minus 2, and you can see here, so here's my f, so here we go, boom, okay, so that's my f. I'm just taking the time to highlight that f again, and then if you draw L also, again here, boom, okay, you see the line, and you see that the equation minus 2x is actually a tangent line to the function x squared minus 8x plus 9 at the point 3 minus 6. So you can see it visually. This line is spanking that function at that point. So it's really doing exactly what it's supposed to be doing. Let's do another example. Suppose the function is the square root of x. Let's find the equation of the tangent line of that function at x equals 4. And then let's draw the tangent of that function on top of the graph of the original function. So the solution, again here, the first thing I like to do is to first compute the output. So here, f at 4 is the square root of 4, which is simply 2. Then I compute my derivative, f prime. The derivative of the square root function is 1 over 2 square root of x. As soon as I have the derivative, because we're asked to do our stuff at 4, I compute the slope, so I know that m is going to be f prime at 4, which is 1 over 2 square root of 4, which is equal to 1 over 4. So I have my slope. So at this point, what do I know? I know I'm looking for the equation of a line. So we're trying to compute the equation of a line. And we know the slope is 1/4, so it's of the form 1/4 x plus b. We still don't know what b is, but we know that this is passing by the point 4, 2. So by replacing x by 4 and y by 2, we can compute b. So this will become 2 is equal to 1/4 times 4 plus b. So if you isolate b here, you'll get 2 minus 1. So b is equal to 1. Now I have my value of m, my value of b. So therefore, final conclusion here, boom. So the L of x is 1/4 x plus 1. So that's the equation of the tangent line of the function square root of x at x equals 4. Let's look at it visually. So here we're starting with the square root function here in red. So I'm going to highlight it in orange. Here we go, boom. So this is my square root function. We're starting at x equals 4, so might as well represent that point here. So if you draw the point x equals 4, so here we go, boom. So that's the point x equals 4. So when x is 4, y is equal to 2, and then the function that we just freshly computed is the equation of the tangent line of that function at x equals 4 that we just freshly computed is the following. So here we go. So here we go, boom. So here in blue, and you can really see that this 1/4 x plus 1 is really first and foremost the equation of a linear function. And that linear function, when it's drawn, so we have two functions here, f and l, but when you draw the function l on top of f, it is really a line that is tangent to that function. So it's really doing exactly what it's supposed to be doing. All right, so why do we care about the equation of the tangent line of a function f of x at x equals a? It's because we can use it to approximate outputs for that function around that point. What I mean by this is that if you pick a value of x close to x equals a, and you compute the value of f at that point, or you compute the value of L, the equation of the tangent line of that function at x equals a, you can see that the outputs of the two functions are very, very close. Like for example, here visually, boom, you see here for that x, the y value on L or the y value on F are really, really close. Of course, as you go away from x equal a, this difference gets larger and larger. But around x equal a, you can see that the two functions are very, very close. This idea is called the linear approximation. L is the linear approximation for f of x. And here, the most beautiful part of the linear approximation is that if you're trying to compute outputs for f, in general, f can be a very complicated formula, and getting outputs for f can be very, very, very difficult. But L is a linear function, one of the easier type of function that we study in mathematics. So computing outputs of lines is something that we can do typically without using a calculator. So we can summarize this by saying that f of x, the function f of x, is very close. So we're going to use the approximation symbol to the function L of x. And we know that L of x is just a function of the form mx plus b, where m is the slope and b is the value that you need so that it passes through a f of a. So let's do an example where we can use that equation of the tangent line to approximate outputs for f around a point. So let's go back to that square root function around 4. Let's compute the equation of the tangent line of the function square root of x at 4 that we already did. And now let's use it to approximate the square root of 5. So we already know. Okay, so from the previous example, we know, so we don't need to redo it here. So we know that L of x is equal to 1/4 x plus 1. So what we want to do here is we want to approximate square root of 5, which is, of course, the value of the function at 5. And now what we're going to do, we're going to simply say that we know that this is going to be very close to the output of the line. So square root of 5 is a creepy number. That's an irrational number, like it's a number with infinitely many decimal places. But now if we compute L at 5, so be careful with notation here. So f, the square root of 5, so f at 5 is very close to L at 5, and L at 5 is, of course, using the equation here, 1/4 times 5 plus 1. And here, without using a calculator, 1/4 times 5, that's 1.25 plus 1. You get 2.25. So computing outputs of a line, so make this an habit of yours to compute outputs for L without using a calculator to really appreciate that these are simpler function, very easy to compute outputs. So we have like 2.5, and here as a remark, just to show you the relationship between the real value and the approximation that we just got. So remark here, if you do compute the square root of 5, you're going to get 2.2360. So 2.25, something that we were able to compute very casually versus the actual value, 2.2360, we're very, very close. We're within like 0.02 units from each other. So we have something very, very close. And actually, the calculator does not know the exact value of square root of 5 because its decimal representation is infinite. It's actually just a very good approximation, better than ours. But actually, the way you get to 2.2260, etc., is by constructing approximations that use more than one derivative. This is called like a Taylor polynomial. This is not the subject of this lecture, but this value is actually constructed using these linear approximation as the basic idea. So it's like the first step to actually understand where or how is this calculator computing a better approximation than us. But anyways, this is like super cool stuff. Sorry, I got excited there. Let's do another example. Actually, just a small remark here. In a true question, in a true application setup, we could say like, hey, we want the square root of 5. And of course, you realize the square root of 5 is not a nice number. But the question would be like, well, what would be the input close to 5 for the square root function that is such that we can compute the square root without using a calculator? And here, the best square, the one that is closest to 5, is actually 4. We know how to compute the square root of 4. It's very close to 5. So we can compute the square root of 4, and it's simply 2. So what you do is you construct the equation of the tangent line at 4, because at 4, things are nice. And then you just extrapolate using the equation of the tangent line to get to 5. So sometimes you have to come up with your own starting point to construct a good approximation. All right, let's do another example. So let's compute the equation of the tangent line of the function f of x equal to ln of x at x equal 1, and let's use it to approximate ln of 1.1. Again, here, a quick remark. The reason why we're starting at 1 is because ln of 1, it's one of those outputs that we know it's very well for the logarithmic function. We know ln of 1 is 0. But ln of anything else, very creepy. Okay, so ln of 1.1, I don't know. Okay, creepy, creepy, creepy. But anyways, so let's construct the equation of tangent line of ln of x at x equal 1. The first thing I like to do is just to compute the output first of the function, so ln of 1, just to really fully understand that we're starting somewhere nice, so ln of 1 is 0. No calculator needed here. Then you compute f prime. The derivative of ln of x is 1 over x. As soon as you have f prime, you get your slope for free by computing f prime at 1. And here you get 1 over 1, which is 1. So therefore, at this point, our linear equation is of the form 1x plus b, and it's passing by the point 1, 0. So when x is 1, y is 0. So you plug this information inside. Here we go. So you plug this information inside. So when x is 1, y is 0. So we plug everything. So plus b. So when you isolate b, you get minus 1. Therefore, our linear equation, L of x, is 1x minus 1. So that's the equation of the tangent line of ln of x at x equal 1. So now let's use that equation to approximate an output for ln at 1.1. So here, what do we want? So we want ln of 1.1. So that number, ln of 1.1, is creepy. It's the output of f at 1.1. Difficult to compute, but this will be very close to the linear output, so the value of L at 1.1. So this is equal to 1.1. I'm using the freshly computed L here, minus 1, so you get 0.1. So my approximation for ln at 1.1 is 0.1. And again here, it's really cool to compare what we're doing versus what the calculator is doing. So here we go as a remark here, poof. So the actual value or the approximation given by our calculator for ln of 1.1 is 0.09531. So you see here 0.1 versus 0.09531, very, very close, within 100th of the real value. So very good just for a linear approximation. And again here, I'm going to just draw visually what's going on here with the function ln versus the linear approximation. So here, poof. Okay, so remark here, what I've done for you, I've drawn the function ln of x. I also drawn the equation of the linear approximation at x equal 1. And then what I've done is I've just labeled in purple the value 1.1, close to 1, and if you compute the output of ln, the 0.09531, versus the output of L, which is 0.1, they're super close to each other. And of course here, I kind of blew up out of proportion what's going on. They're actually way closer than that, but you get the idea. These two functions, L of x and ln of x, very, very close, around 1, so you can approximate outputs of that function around 1. And again here, why around 1? Because we know how to compute the output of ln at 1. It's 0. So you can do this without using a calculator. So very powerful linear approximations in order to estimate or approximate outputs around a point. And the key idea here is, of course, computing derivative to get the slope. Then you get the b just by knowing where you are on the Cartesian plane. And then you need to understand that nearby, so around A, you can use L to approximate F. And one thing that you should be able to master also is if you have just an approximation question, you should know how to find your own A to start the whole process. All right, for that question, that's it, that's all, okay? Not that question, but for that section, that's it, that's all. Bye-bye, là.